As we approach the speed of light, embarking on a spacecraft that drifts away from Earth and accelerates incessantly, we encounter a series of intriguing phenomena. Exploring these questions leads us to delve into the fascinating mysteries of the universe and dive into the concepts of special and general relativity. Initially at rest, our spacecraft begins to accelerate after launch, propelled by a propulsion system capable of gradually increasing our speed. As we move away from Earth, accelerating more and more, one might assume that the speed would become unbearable. Surprisingly, the speed itself does not affect our bodies. Inside the ship, we don't perceive its speed, but rather the acceleration that pushes us against the seats, provided by the reactors. As long as the thrust is reasonable, we can comfortably endure it throughout the journey. However, as we approach the speed of light, there is the danger of collision, where something as small as a grain of dust can cause devastating damage if it hits the ship. Fortunately, our spacecraft is equipped with a force field that repels dangerous objects, allowing us to navigate freely through space. As we accelerate, an optical effect becomes apparent. The stars ahead, which seemed close, gradually drift away, giving the sensation that the sky is shrinking before us. This phenomenon is similar to the perception of rain while driving at high speed, where the drops seem to fall straight ahead as we accelerate. Thus, as we explore the effects of approaching the speed of light and surpassing it in the concept of space-time warp, we encounter a universe full of surprises and challenges that defy our conventional understanding of reality. As our spacecraft traverses the cosmos at speed, the light that shines upon it assumes new properties. This is the aberration of light. As we advance, the light ahead of us intensifies and focuses, while the sky behind us expands and darkens. This phenomenon culminates in a unique optical distortion. As they theorize about crossing an immense cosmic mesh symbolizing space, under normal conditions, we would expect to see in orthogonal structure straight lines converging with the horizon, due to perspective. However, as we hurry at almost luminous speed, the effects of this aberration alter the view of these lines. Like passing through distorted lenses, the mesh seems to bend forward, and the objects we cross seem tilted toward us. This effect is known as Penrose rotation, a fascinating illusion where perspective is viscerally altered. When discussing astronomical distances, we inevitably encounter the Doppler effect, the idea that when we observe space, we are actually peering into the past. This is because the light from a distant star travels billions of kilometers before reaching our eyes. When we observe it, we witness the star as it was at the moment of emission of that light, perhaps thousands of years ago. Inside our ship, we apply this notion as we distance ourselves from Earth. Earthly light takes progressively longer to reach us, which, through a hypothetical super telescope, would make us see the planet and its inhabitants moving in a kind of slow-motion playback of the past in real time, revealing the relativity of time and space as we venture into the vastness of the universe. The Doppler effect, usually associated with sounds, also applies to light when we are in relative motion to a light source. As we move away from Earth, each tick of Earth's clocks takes longer to reach our ship, making the rays of light seem to arrive in slow motion and with less intensity, resulting in what is known as redshift, where the light appears to shift toward the red end of the spectrum. The image of the planet not only diminishes in intensity, but also changes its color due to this lower frequency of the observed light. Ahead of us, on the other hand, the ship encounters the light from the stars, making them appear brighter and shifting towards the blue end, known as blue shift, where the wavelengths of light are apparently compressed. Additionally, the clocks of the stars we encounter would seem to tick faster than ours. With precise instrumentation, we would be able to measure both aberration and Doppler effects from the beginning of our acceleration in space. But it is crucial to understand that these effects do not represent actual physical changes in the observed objects. They are optical illusions based on our perception of moving light. As the days pass and the ship approaches the speed of light, however, we move from optical illusions to real physical effects described by Einstein's special theory of relativity. In special relativity, time is relative and depends on the observer's motion. If we move at high speeds relative to Earth, we experience time dilation. The clocks on the spacecraft would run slower compared to clocks on Earth. Therefore, if we were to return after a long space journey, we would have aged less than people who remained on Earth. Along with time dilation, there is length contraction. Objects appear shorter in the direction of relative motion at the speed of an observer. In other words, if we could observe the spacecraft as it swiftly passes by us, it would appear shorter than it is when it is at rest. These phenomena aren't mere illusions. They're physical realities of our universe. Special relativity reveals that as we approach speeds close to that of light, space and time, as we know them, begin to behave in non-intuitive ways. The very nature of the fabric of space-time alters due to extreme motion. Length contraction is one of the fundamental pillars of Albert Einstein's special theory of relativity. And yes, it is a real and physical phenomenon, not an optical illusion. According to this theory, as an object approaches the speed of light, its length in the direction of motion will be contracted. That is, it will shorten for a stationary observer. For the occupants of the spacecraft, however, it's as if the universe ahead of them is compressing. This means that the distance to a destination, like a distant star, could effectively seem shorter for those aboard the high-speed craft. Thus, relative to the travelers, the duration of the journey could be much less than the time measured by observers on Earth. Therefore, in theory, and according to Einstein's relativity, it could be possible for a space traveler to cover distances of thousands of light years in a considerably reduced amount of time from their own point of view. For someone on Earth, however, many years would have passed due to time dilation, another aspect of special relativity. The relativistic observation of contraction and rotation also introduces the effect known as Terrell-Penrose rotation. This occurs when an object passes by rapidly and appears to rotate due to the way different light from its various parts reaches the observer. The part of the object that is farther from the observer emits light that takes longer to arrive than the light from the closer part. This can make the object appear to rotate. In special relativity, these aren't just curiosities. They're manifestations of the fundamental structure of space-time that affect all measurements and observations. Length contraction and time dilation are interconnected, and both result from the limitation of the speed of light as a universal constant. For us, travelers in the ship, our field of view and the entire perception of the universe dramatically changes as we approach relativistic speeds. The speed of light in a vacuum is approximately 299,792,458 meters per second, and it's considered the ultimate speed limit in the universe according to the laws of physics as understood today. In special relativity, the speed of light is not just a speed barrier. It's a fundamental constant that separates causes from effects, the past from the future. The speed of light is the same for all observers, regardless of how they or the light source are moving. This brings a set of non-intuitive consequences to our understanding of space, time, and energy. As an object approaches the speed of light, its effective mass increases according to the relation E equals mc, where E is energy, m is mass, and c is the speed of light. This means that to accelerate even closer to the speed of light, more and more energy is required. In fact, it would require an infinite amount of energy to accelerate a mass that has a non-zero amount at rest to the speed of light, which is impossible according to current physics laws. Even if we can never reach the speed of light, we can theoretically get very close to it. If we did, as described in your question, we would see extreme effects due to very fast motion through space. The field of view would become distorted, with light reaching the spacecraft concentrated in a bright circle in front and darkness around. This phenomenon is known as apparent blue shift in front and redshift behind, a result of Einstein's special relativity and the relativistic Doppler effect. In simple terms, while to an observer on Earth, we seem to be approaching the speed of light, for us in the spacecraft, it would always seem that the speed of light is out of reach, and we wouldn't perceive any change in our own speed relative to the light around us. The visually observable universe would shrink into a tunnel ahead of us, and all objects would move through that tunnel, from our perspective, in a blink of an eye. This discussion places us in the realm of theoretical physics, where concepts like space-time, relative velocity, and the nature of light are complex and often counterintuitive. The predictions of special relativity have been confirmed in many experiments, but direct human experience is far from the extreme situations where these effects become evident. What you described is a concept often explored in science fiction known as warp drive or a warp unit. It's a hypothetical theory based on mathematical solutions to Einstein's general theory of relativity. The idea behind warp drive is to alter the geometry of space-time in such a way that space compresses in front of a ship and expands behind it, allowing the ship to effectively move faster than light without locally violating the speed of light within its own bubble of space-time. This bubble would be a region of space-time that is distorted in such a way that while the ship itself would remain stationary inside it, and thus not experience relativistic effects like length contraction or time dilation, space itself would move, carrying the ship along with it. The ship wouldn't be moving faster than light relative to the space around it, but space could move faster than light. This is comparable to a treadmill. You can walk at a reasonable speed on the treadmill, but the movement of the treadmill can take you to your destination faster than if you were walking on the ground. The theory generally assumes the existence of a theoretical form of energy or matter with exotic properties, exotic matter or negative mass, that we don't observe in the universe, and that would have anti-gravitational properties, meaning it would curve space-time in the opposite way to traditional mass and energy. These concepts remain highly speculative and are beyond the current engineering or scientific observation capabilities. Visualizing what would happen from the perspective of someone outside or inside a warp drive is equally speculative. Some of these effects, like the concentration of light into a bright point in front and complete darkness behind, are analogies drawn from how we think light interacts with extreme distortion of space-time. Though it's exciting to speculate about these topics, it's important to note that warp drive remains, as of now, a theoretical construct without experimental or observational support, and with significant theoretical challenges that have yet to be overcome. Modern science doesn't yet have a clear path to the practical viability of a warp drive, and the concept remains firmly entrenched in the realm of science fiction and advanced theoretical speculation. So, now you have a better idea of what science has to say about faster-than-light travel through warp drive, a fascinating intersection of general relativity and human imagination. While it still firmly resides in the realm of science fiction, and the laws of physics as we know them haven't been broken, the ongoing pursuit of knowledge leads us to question and sometimes rediscover what we thought was possible. Remember, science advances at the edge of the known and the unknown, and every question answered leads to many more questions. Perhaps one day, with the evolution of physics and technology, we'll look back on this video and reflect on how it represented only the beginnings of our journey to the stars. Don't forget to like this video if you enjoyed the journey through the warp drive universe. Share it with friends who also love science and fiction, and subscribe to the channel if you're not already subscribed. Oh, and if you have any ideas for what you'd like to see explored in future videos, please leave a comment below. We love to read your theories and insights.